So we have a 63.5 centimeter guitar string. So let's get your guitar string. And it is tuned to produce a note of B3 at 245 hertz. Find the speed of the transverse wave on the string. And then part B, if the tension of the string is increased by 1%, what will the new fundamental frequency be? Here, if the speed of sound in the surrounding air is 344 meters per second, find the frequency and the wavelength of sound wave produced by the air, produced in the air by the vibration of the B3 string.
Okay. For the speed, V equals.
These are standing waves. Remember those equations we came up with for lambda for standing waves? When n equals different things.
So then you can have 2L times F1 equal V.
Yeah, okay, good. And
then just plug in. They give you your F1. It's 245 hertz. So you do 245 times 2 times 0.635.
okay. All we're doing to get this equation is using the lambda n equals 2L over n, all right? Where yeah, it stands for the number of nodes that you're putting in. Okay, so in this case, our node was what? 1, right?
Mm-hmm.
So then we have lambda equals 2L. And then what else did we know? We knew that velocity equals lambda times frequency, right?
Mm-hmm.
And if you put that 2L there,
is equal to L times frequency. Okay.
Okay, so I don't want you to think that this is a set equation. It depends on what n is.
Mm-hmm.
If this was 2, then lambda would just equal L here. Are you with me or not?
Yes.
Okay, so now that we got that part down, what do we need to do?
So just plug into L and F. Got 311.15.
Good, 311. All right, so let's look at part B. What is part B? It says the tension goes up by 1%.
Got a 1% increase, so that's what's throwing me off. It's 1% increase.
Yeah, this is a little tricky because we weren't ever given what the tension value was, right?
Yeah.
So what we can do is we can just assume if the initial tension was 1 unit, the new tension is going to be 1 plus 10% of that unit.
Mm-hmm.
So 10% is 0.01. So that would be 1.01. This is 10% of the tension. All right. So then when we look at the frequency in relationship to the, I'm sorry, am I boring you?
No, sorry.
The fundamental frequency is proportional to the speed. Okay, so if we know it's proportional to the speed, then it's going to also be proportional to the square root of the force.
Mm-hmm.
So if we take the frequency and we multiply it times the square root of the force, and that should give you 246 hertz.
Makes sense.
A little tricky. All right, so part C, we want to know what the frequency of the sound wave was that was coming off of B3. Okay, so we're trying to see how does it compare to the, how do these compare to the frequency and wavelength of the standing wave on the string? That's the question. All right, so what we would need to do is calculate what the wavelength is in the air. So how would we do that?
Wavelength in the air?
Just take the speed of sound and divide it by the frequency, right? Because we know velocity is equal to lambda f. And if we divide by f, we get lambda. They just gave us the velocity of the sound traveling the air.
Then we have frequency.
Yeah, so just divide.
Hmm.
Do you understand?
245, yeah.